Good evening, everyone, and welcome to our final discussion session for the Physics of Nanoscale Devices NPTEL course. As always, seems like I advanced the date by a few millennia. Yes. So, yeah, as always, I'm Jyotishwaran, a PhD student in the Electronics and Communication Engineering Department of IIT Roorkee. So in this last session, we are not, of course, we are not going to be covering anything new. Uh, what we are essentially going to have is a course summary from beginning to the end. So these are slides that I keep making over time, summarizing all the important results. So the aim of this session is to kind of give you a single place where many of the results are presented in a consolidated fashion, and rather than just I could have simply copied the contents from the lecture slides and just compiled them into a single presentation, but I do not want to do that. In this session, what we shall be doing is, like, I will not be presenting every single result that is relevant, but I'll be presenting the ones that I think are important and will emphasize on the things which, in my opinion, are crucial for solving the questions in your upcoming examinations. So by now, I guess all your assignments and stuff should be done. So that's half of your evaluation. So this is for the rest. So we shall be looking at the topics in the following order. We shall be looking at the basics, which is the quantum mechanics intro and the Kronig-Penney model. Then we shall spend some time on density of states, Fermi distribution, and then the Landauer theory of transport for the two-terminal devices, where we shall consider ballistic and diffusive transport, and then we shall look at MOSFET characteristics for the classical bulk MOSFET and the ballistic MOSFET, and then MOSFET electrostatics, and then double gate devices, strain engineering, the things that we covered in the past couple of weeks, and finally quantum dot devices and thermoelectric effects, which were the topics covered in the most recent session. So to begin, when we are looking at the Schrodinger equation, the 1D Schrodinger equation is given by this form. The Hamiltonian operator applied to the wave function psi of x will give me the energy multiplied by the wave function. So this is an eigenvalue equation. And so this is the time independent Schrodinger equation, just to make things clearer. There is a time dependent version of this equation, but that is not relevant for this course. So this is the time independent Schrodinger equation, where we are talking about the eigenstates or the eigenfunctions of the Hamiltonian. So the Hamiltonian for a 1D system is given by this form, minus h square upon 2m times d square by dx square, the second derivative in the length dimension, plus v of x. So we take the second derivative of the wave function, multiply it by this negative constant, and then take the product of the wave function and the potential, 1D potential. And it is said that if psi of x is an eigenstate of the Hamiltonian, then it will satisfy the Schrodinger equation. So the next thing that we saw was an application, a straightforward problem, the particle in an box. This is alternatively known as the infinite well problem. So the infinite well problem, again, I'm not going to walk you through the solutions. We know that the energy levels are quantized here. So yes, so the important takeaway from this, which we have been using all the way till the very last uh, topics covered in this course, is that when I introduce confinement into a system, there is going to be quantization of the energy levels. In fact, there is going to be quantization of pretty much every physical parameter. Okay, so the energy levels are given by this expression, n square pi squared, yeah, this should be h bar squared. Uh, Just one second. Because it's h squared k squared by 2m. So yes. And we know over here, just for the sake of completeness, n is equal to 1, comma 2, comma 3, all the way till infinity. And the wave function is given by square root of 2 upon L sine n pi by L times x in the region 0 to L. And outside of the potential well, the wave function is 0 because we have infinite potential values to the left and right of the well. And in our convention, we assume that the left boundary of the potential well is at x equal to 0. Alternatively, we can also take the central value here, in which case we will have a slightly different form of the wave function. But the functions themselves, the graphs of the functions will still be the same. So the thing that we need to understand over here are how to apply boundary conditions. And in the boundary conditions, the things that we care about are continuity of the wave function. This is far more important than the continuity of the derivative of psi of x. And then we take care of normalization of wave functions. So essentially, we take the mod squared. So the normalization criteria is given by this expression, integral mod psi of x whole squared dx should be equal to 1. Okay, so these are the things that you need to remember, or that will be helpful to keep in mind while you are considering the very first part, the basics of quantum mechanics. And then we move to the chronic penny model. The chronic penny model, just again, I will add for clarity some more points here. We have v of x is equal to v of x plus a, and the potential is given by this. Here we go again. But well, this will be the last time I struggled to draw graphs, well, in front of all of you. I guess this will be a lifelong struggle for me as long as I'm teaching in the online. Yes. So if we have this, then the potential is going to be, let me say A is somewhere over here. So this is x and this is v of x. So I'm going to have a potential like this. This is what we considered in the chronic penny model. Yes. So we have some v naught from 0 to some point b, and then from b to a we have v of x is equal to 0. So this was the kind of potential that we considered, and of course this repeats with this relation, v of x is equal to v of x plus a. So we get the transcendental equation, which is plotted like this, and then we look at the boundary conditions. So on the left-hand side of this equation, there was a big transcendental function which had hyperbolic sines and cosines, and on the right of it, we essentially had cos ka. So this is plus 1, and this is minus 1. So essentially, wherever this function takes values between plus 1 and minus 1, we will take the allowed values of energies. So this is the normalized energy value. Let me use a different color here so as to distinguish. So this is the normalized energy value. Yes, and oh yeah, there is one part that I missed out here. So let me just make a new slide and come to it in just 1 minute. And then we will go. So let me just take a step back for a second and say thing for this is Bloch's theorem. So if v of x is equal to v of x plus a, then any solution psi of x that satisfies h psi of x, which is given by minus h squared upon 2m e. Oh, why did I write psi of x plus a there? V psi of x is equal to e times psi of x will have satisfy the following conditions. So these are the different ways of stating the Bloch's theorem. First part is psi of x plus a is equal to e to the power I k a times psi of x, or not or, and. So both of these conditions are equivalent. Psi of x is equal to e to the power I k x times u k of x. So this function u depends on k such that uk of x is equal to uk of x plus a. Mind you, the wave function itself is not periodic. So if I go take psi of x going to psi of x plus a, then so you can just quickly look at this here. So this implies psi of x plus a is equal to e to the power I k x plus a uk x plus a, which since uk of x plus a is equal to uk of x, this is going to become e to the power I k a times e to the power I k x uk of x. This is what I already know to be psi of x. So these two conditions are equivalent. So I shouldn't even write and here. These two conditions are equivalent to each other. One implies the other. So remember what you are writing on the left side when you are looking at questions. Remember which form of the Bloch's theorem is given to you. Okay, sometimes we may just write psi of x is equal to e to the power I k times uk of x. At that time, you need to know that that is the wrong representation of the Bloch's theorem. Okay, so uh, I promise that I will give you a rough sketch of the proof for Bloch's theorem, at least for this case. I can sketch that right here. So all you have to do is substitute psi of x by psi of, or rather, change x by x plus a, and then see what happens to this differential equation. You'll see that every term will get an x plus a, and d square by dx square is going to remain the same, because changing x linearly does not change the differential operator. So you are going to have psi of x plus a here, but v of x plus a will end up becoming v of x again because of the periodicity criteria. So then you can take the difference between these two equations and kind of see how to get psi of x plus a from psi of x. So we will be using a form of the Taylor series, and using that you can essentially prove this part. by comparing the coefficients of the equation, you can show that yes, this is how the wave function will look like. This is the only form the solution to the Schrodinger equation under the periodic potential can have only form of solution that a particle in a periodic one-dimensional potential can have. Okay, so now using Bloch's theorem, we come down to the chronic penny model. So the things to remember in the chronic penny model are, so these are the bands represented in the reduced representation. Always remember the band gap is the smallest energy separating the bands, not the larger energy. So you should not take this and this energy and cite this as the band gap. No. For these two bands, the band gap is here. For these two bands, the band gap is over here. Okay, so always identify HOMO and LUMO, which is the highest occupied molecular orbital, essentially the highest occupied band, and the lowest unoccupied band. So this will be if this is the highest occupied band, then the band immediately after that is going to be the lowest unoccupied band, and the band gap for the material is going to be the gap between those two spots, those two molecular orbitals, those two bands, the minimum energy. So as the energy increases in the chronic penny model, the bands become broader and broader and broader, and the band gaps become smaller and smaller and smaller. What do I mean by bands become broader? More energy levels start getting allowed into the bands. So this curve is not too deep here, but in the next band you can see that the more in like this is a longer curve fit into the same length area. This is further longer. This is the curve above that will be longer, and so on and so forth. And the reduced zone representation will always have for a 1D lattice is always going to be from minus pi by a to pi by a. These are the k values. So this is essentially the reduced EK relationship, and a is the period of this lattice. Another point that needs to be mentioned here is open up a new slide. Another point that needs to be remembered here is the notion of effective mass, also introduced in these discussions. So what is the effective mass? So remember the picture that I discussed in the last session. So any particle, you know what? Just give me 1 second. Should be able to just open the previous slides and copy that into this. Just give me 1 second. Yeah. Yep. So this is essentially what we do in the effective mass representation. I copied the effective mass title again. So yeah. Okay. Let me just remove this. Yeah. So okay. So if I know the EK relationship, if EK relationship is known, if the dispersion relationship is known, so if EK relationship is known, then uh, the effective mass m star will be equal to upon d squared E upon dk squared at the band minima and maximum. So this is not a universally valid relation. This is valid only at the band minima and maxima, because as you can see, the derivative, first derivative is 0 at the minima point here and 0 at the maxima point here. But the second derivative will be positive at the maxima point and negative at the minima point, which means somewhere in the middle it will take a 0 value. So somewhere in the middle point, the effective mass as calculated by this relationship is going to be infinite. So this also tells us, so this quantity is the inverse of the curvature. So this is inverse of the EK curvature. A more detailed explanation I've covered in the older session. Please go back and refer to it. So EK relation curvature. Okay, and what does the effective mass tell us? It tells us the following. The most important takeaway here is only electrons near the band edges. So these two quantities, band minima and band maxima. So this is what we call the band edge. Near the band edges, participate in transport. So yes, in general, let us say I want to understand the magnetic properties of a material, then yes, I need to be concerned with every single electron present. I need to look at the entire EK relationship, things like spin orbit coupling, fine structure, hyperfine structure, and all of those things. But if I only need to understand the transport properties, wherein the response of the system to an applied voltage, then I only need to be concerned about the electrons near the band edges transport. So what do I mean by transport? Here by transport I mean current carrier or current conduction. So in most cases that is true. In some cases, yes, the other electrons that are not participating may still have some interaction, but that is for what to say, like non-trivial materials and some specialized structures where I have some different heterostructures and things like that. But in most standard cases, this is all that we are concerned about. So ready, come on. Every other line came easily enough. Yes, there we go. Yeah. So this is the important takeaway from our effective mass discussion. So this is the expression for the effective mass. So if you are given an EK relationship, this is how you find it. But remember, this is only at the band edge. Let me also explicitly state that condition here. This is only valid at the point where dE upon dk is equal to 0. Okay, so yeah, that's that. And then we move to our second topic, which is where we started looking at materials. So we have the density of states. I'm not giving the exact expressions. Please go back and read your slides for that, so that you know there is some reason for you to go back and look at the slides. And that is another reason why I don't throw all the results in here, because I want all of you to go back and read the slides and look at the lectures. A few more times before you give your exams. So, but here, in general, the 1D density of states is proportional to 1 upon square root of E. 2D density of states is not proportional, is independent of the energy. The 3D density of states is proportional to the square root of the energy. So roughly sketched, the graphs are going to look like this. Here, yeah, as you can see, I'm assuming that there exists an EC. So everything below EC, there are no energy states available because they are in the band gap. So above that, we have these relationships. So that is basically all you need to remember. And in most problems, as you have seen, we only consider the 2D or quasi 2D systems. So the density of states is going to be given by this expression here. G2D is equal to n star divided by pi h bar squared. So that is that. Then we have a look at the Fermi distribution. So the Fermi distribution function is given by this 1 divided by 1 plus, I think I can make it slightly neater. 1 plus e to the power e minus ef upon kBt. If ef is equal to half at any and every temperature. So if you have the, just for the sake of trivia, the Bose-Einstein distribution function, this plus is replaced by a minus. And if you have the Maxwell-Boltzmann statistics, I assume that the temperature is very, very high. So, well, technically speaking, both Bose-Einstein and Maxwell-Boltzmann will kind of uh, converge to the, you know what, I shouldn't, have I written this as EF? Oh, ET, yes, yeah, this is ET, but I can just, make the situation slightly better and call this the mu. So this is the chemical potential. Now it starts giving me default lines. No, I don't want that. Yes, E minus mu divided by kBt. And the Maxwell-Boltzmann distribution is E exponential of minus E divided by kBt. Okay, so at t equal to 0, I have the flat curve, which is 1 all the way till the Fermi energy and then immediately drops to 0 above the Fermi energy. At t greater than 0, we have this kind of a distribution, and we know that this has the following symmetry: f of e minus ef is equal to 1 minus f of e plus ef. Again, this is valid at all temperatures. It is quite easy to see here also. Like essentially, I have this step function about the ef value, and as the temperature increases, the step function softens and essentially becomes flatter and flatter and flatter. So integral 0 to infinity of fd of e is 1, which I also sometimes write as minus infinity to infinity, depending on my energy scaling, you know, how I scale my energy values and what kind of reference energy points that I have set. So this is the basics of the Fermi distribution function. About the Fermi energy, we will come back to it slightly later. Okay. So the next topic that we saw was the two-terminal devices and the Landauer theory of transport. So this is terminal 1, terminal 2. I apply voltage at terminal 1. Terminal 2 is assumed to be grounded. There exists a ballistic channel. So here, this is a ballistic channel. So here the stored charge in the channel, number of electrons is given by density of states of the channel. So this is number of electrons. Let me just be clear here, in the channel. And So yeah, why really? So yeah, so that is density of states of the channel. So again, most if not all of you already know it, but I'm just mentioning it to be completely clear of the channel. And F1 and F2 are the Fermi distributions in the two electrodes. So both the properties are combining here, D. So this is the charge stored. The current across the channel is given by D of E into pi into gamma of E. Here gamma of E is the energy broadening. So this is equal to H divided by tau of E, where tau of E itself is the transit time through the channel. Okay, so and the product of these three terms is essentially what we call the mode density function. So this is M of E, number of modes available at a certain. Oh, I've already mentioned it here, so I can remove the clutter on the slides. And the current expression at 2q by h is the constant that is seen there. So if I try to include diffusive effects, then I kind of introduce the transmission coefficient to this, and the transmission coefficient depends on the de Broglie wavelength at a given energy. So T of E is going to be lambda of E divided by lambda of E plus L, where L is the channel length. So that I can mention up here. This is the length of the channel. So for very small lengths, where the length of the channel is significantly smaller than the de Broglie wavelength at the relevant energy levels, the transmission coefficient can be approximated to 1. Essentially, the transport is purely diffusive. Let me make this slightly neater. HB. So, but for very large, I think this can be written slightly better. Yes. So for very large lengths, T of E can simply be written as lambda by L. So I can just ignore the lambda in the denominator because L is significantly larger. So this is approximately equal to lambda by L. Okay. You know what? Better approximation symbols. Okay. So now we move to the, like we are still talking about land hour transport. So in ballistic transport, there is no scattering in the channel. Energy loss occurs only at the interfaces. So the energy loss, half of the energy loss occurs at the channel one, terminal one channel interface. The other half occurs at the channel terminal two interface. So special conditions where we consider these expressions is when F1, F2 minus F1, when the applied voltage is very small. For the low bias condition, we have this relationship. So this is going to be dou F by dou EF into Q times dV. Dou F by dou EF can alternatively be, it'll actually be minus dou F by dou E, which we can write it as dou F by dou EF. So, wait a second. Yeah, I'm kind of messed up. So yeah, so dou F by dou E is the Fermi window function. But when we are writing this, I can essentially, uh, yeah, I can essentially put a put an EF over here because and not using the negative sign. Yes. So I can take the Q outside. So this gives me the quantum of conductance at t equal to 0. This Fermi window function is given by the negative of the Dirac delta function. So minus, so dou f by, so this is minus dou f by dou e. So it will look like this. As the temperature becomes smaller and smaller and smaller, this will become a spike, a single spike, Dirac delta function. Okay. So, and furthermore, when we consider the low bias, low temperature criteria, remember the Fermi window function becomes the Dirac delta function. Since that is the case, then the integral is just dropped. So in general, this is going to be the expression 2q squared upon h into the transmission coefficient at the Fermi energy multiplied by the number of modes at the Fermi energy multiplied by the voltage. So this is going to be the current. I by V is going to give me the conductance. So that is going to be this. Depending on the channel length, this may be 1, this may not be 1. So one takeaway here, which I shall write at t equal to 0k, only electrons near the Fermi level contribute to transport. Very near. Contribute to current conduction. Okay. So another, relationship that we have is the relationship between Kf, the Fermi momentum or the Fermi wave number, and the surface charge density. So for a 2D system, this is the relationship. Or alternatively, I can say uh, yeah, 2ns by pi whole power half. Yes, this is, I mean, I cannot alternatively say this in any other way. So how do I get this? I get this from this expression, h square kf squared divided by 2m is equal to ef. Then we move to the phase space, k space, and then, compare the areas and volumes of or rather the area in this case. So for a 2D system, we have this relationship. What it was in the case of a 3D system was solved as one of the assignments. So please, not assignments, discussion problems during the session. So please go back to that and look those results up. And in a 2D channel, additionally, we know that the number of modes at a given energy is the number of half wavelengths that fit along the channel width. So that is W is equal to lambda dB divided, the number of modes is equal to W divided by lambda dB by 2. Here, lambda dB itself will be H divided by the momentum, which is going to be square root of 2m star e. Okay, so, and finally, the mode distribution function and the Fermi integral. So the mode function essentially has this dimension. It has the density of states multiplied by the inverse of the transit time. For reference, go back here. I have the energy, its density of states into energy broadening. Energy broadening is inverse of the transit time. Okay. So, and I know that tau of e is always proportional to e to the power half, because this is again going to be something like this, because momentum is mass times velocity. So in fact, if I write this as 2e by m, I will get it as 1 by velocity. So h into L divided by the velocity is going to give me the transit time. Okay, so just 1 second. Yes. So, yeah. So since the transit time is always proportional to e to the power half, the mode density function is just whatever dependence the density of states had multiplied by e to the power half. Therefore, the 1D mode density function is going to be independent of the energy. The 2D mode density function, is going to be proportional to e to the power half, and the 3D mode distribution function is going to be proportional to the energy, e to the power 1. The current is proportional to the integral of m of e into f of e into d. So this quantity is what we define as the Fermi integrals, because this has a proportionality to, so this is proportional to some e to the power alpha, where alpha can be 0, half, 1, and so on and so forth. Therefore, in the 1D channel, the current is proportional to F0 in the high bias case, F minus 1 in the low bias case, because we kind of can take F2 minus F1 and replace it by its derivative. In the 2D case, under high bias, the current is proportional to F half of eta F. The conventions between F and eta, please go back to either the lecture slides or the discussion slides. You will find those quantities in detail. And the low bias case, it is the Fermi integral of order minus half. And for a 3D channel, the current is going to be Fermi integral of order 1. And in the low bias case, Fermi integral of order 0. The relationship for Fermi integrals is when I take one derivative, dou f by dou eta or dou f by dou eta f, then I will move down by one order. So this is going to be Fn will go to Fn minus 1. The constant of proportionality I am not mentioning here. Please look them up. So that is the point. The low bias current expression will always be one order less than the high bias current expression. So this is more or less what is present in, and the transmission coefficient, as you can see, will have no energy like it will not have any explicit energy dependence. What do I mean by that? See, the numerator has e to the power minus half dependence, but the denominator also has e to the power minus half dependence, so they kind of cancel each other out. Okay, so it is effectively just a constant scaling factor. So even if I consider diffusive transport, the Fermi integrals are still going to remain the same. Now, MOSFET characteristics, that was the next thing that we looked at. So in a bulk MOSFET, I would like to see I get to see an IDS versus VDS, the output characteristic of this form, where essentially, I think I can take some time and draw this properly now. So these are things that I kind of sketched very quickly. Yes, so I'm going to have, and I'm not talking about the ideal characteristics, I'm talking about the real characteristic. So wherein I will have a linear region. Slowly I'll break out of that and I will have an eventual saturation. So this will allow me to demarcate the regions as slightly better. So this gives me the linear region, and this gives me the saturation region. And over here, again, I will redraw this graph once I'm done labeling the axis here. Why can't I? Yes. Yeah. So this is VDS. This is IDS. So over here, I'm considering VGS versus versus IDS, and here I'm essentially going to have a curve like this, and this point wherein I have the sharp increase, or rather this point, it's more easy to define this. It's easy to lay down the definition here, so I can say this. So I can say this is my threshold voltage VT, and I can say this is the saturation voltage. So this is VT, and over here I'm in the off mode for the device, or this is also called the cutoff. And over here we are in the active region, active and saturation region essentially. So this is the active. Why am I not able to write a single word? Active, yes, or on. Okay, so this is the relationship between VGS and IDS. I can just select this, drag this. Yep. So the output characteristic and the transfer characteristic. The relationship between VDS and IDS is given by this expression. It's W divided by L, width of the channel divided by length, into the oxide capacitance, which is the capacitance of the oxide layer here. Yes, so I will just quickly label them. So that is the gate, and this is the oxide layer. And source and drain. So typically the source is grounded, and the drain VD is applied there, and the substrate is also grounded. So VGS is the same as the potential difference between the gate and the source. This is just one way of setting up the potentials for the transistor. You know what? I think we can write the equations better than this. Okay. Yeah, what I can see is when I initially wrote these slides and now my handwriting has improved ever so slightly. W divided by L times Cox. So this is typically given per unit area into VGS minus VT. The explanation for all of this, I mean, Professor Vishwendra has given in his lectures, and I have also covered it from my side on the discussion sessions. So, yeah, so ID sat, the saturation current is W divided by 2 L prime times Cox into mu into VGS minus VT, the whole square. Will there be a mu? Hold up. Give me just 1 second. Let me just go back. Oh God, why does every window have to open there? Just one second. Let me verify the expression to make sure I'm not making any mistakes. Oh yeah, of course, the mobility is there. Wait, then am I missing the mobility in the previous expression? Yes, I was missing the mobility in the previous expression. So yeah, it is a good thing that I took the time to double check. I was able to eliminate one mistake in these notes. C ops times mu, because of course I need the mobility. Only then the dimensions will match. So saturation is caused by channel pinch off. Again, this was explained, and the maximum, or rather the lowest possible value of saturation current was also discussed, and it was shown that how this keeps increasing as my drain source voltage keeps increasing. Essentially, the drain kind of lowers the barrier, so I have some kind of a DIBL. So these are the non-ideal effects. DIBL causes channel pinch off and saturation, and there is also what is known as the subthreshold swing, which essentially shifts the current presence when I have, depending on the threshold voltage of my device. So VDS technically affects the effective threshold voltage also. So ideally speaking, subthreshold swing should be less than 6, or rather at 60 millivolts per decibel, essentially in terms of current increase. So per decibel of current increase. Okay. So that has also been mentioned here. Now when we look at the ballistic MOSFET, remember the various Fermi integrals for the current and voltages. Go back and refer to them. And the average velocity in the positive direction. So Vx plus of E. For a 2D system, we know that this is 2 by pi times V of E. For other dimensions, I have done the derivation. The overall average velocity for a ballistic channel can be represented by different Fermi integrals. Even this was worked out, or at least I did it for the semi-classical case and then showed that it would be a Fermi integral. Professor Vishwin had covered the thing in a slightly greater detail. And of course, the current expression remains pretty much the same. The only thing that changes is the number of modes that are available. So what needs to be remembered is, for a bulk MOSFET, we kind of have this kind of a situation where VGS minus VT determines the amount of charge that is present in the channel. Whereas the gate voltage, in the case of a ballistic MOSFET, determines the number of modes that are present in the channel. That is how the current is controlled. So this is not a full-on charge control device like a bulk MOSFET. And as a result, the velocity saturation does not occur due to channel pinch-off, because the phenomenon of pinch-off does not generalize to a ballistic MOSFET. It occurs as a result of velocity saturation. Now, the idea is, initially when there is no VDS, I have a uniformly distributed values of velocity in the channel, assuming that the channel has enough electrons. As I keep applying a higher and higher and higher positive voltage, we can see that this distribution skews. But the point is, there are only so many electrons present in the channel, so this distribution can increase to the positive side by only so much. After that, there is no more velocity increase that will occur by applying VDS, and because of that, the current will saturate. So then we came to MOSFET electrostatics. So this is something that we covered as recent as 2 weeks ago. So the first thing to remember is the idea of channel inversion in a bulk MOSFET, and find out the inversion potential. So the model for the electrostatics is the following. I have Vg and psi s. So this is the surface potential at the gate substrate interface. And in between, there are two capacitances: the oxide capacitance, which is a constant, and the depletion layer capacitance, which is a variable value. Ideally, I will want this depletion layer capacitance to be as small as possible. So The inversion potential is given by this. Psi inversion is 2 kBT by Q log Na by Ni. So this was for an N MOSFET, so P-type substrate. The depletion width was given by this expression. We can use the two to also find out what the depletion potential is. And in the depletion regime, we know that the charge present, the surface charge that is present in the depletion layer is proportional to psi s to the power half. Let me just do a slightly better job here. And since this was done relatively recently, I will just request you to go back and refer to the slides rather than replicate the relationships and the graphs over here. And in the inversion or accumulation mode, E of psi Qs is proportional to e to the power psi s, and in the inversion regime, I also have the same relationship. So that's what I've written here. So when I've achieved inversion or I'm in the accumulation, I have this kind of a relation. So what we see is that inversion, accumulation. Okay, so this means that there is a certain region when I apply a depletion voltage, the behavior of my MOSFET is not symmetric. Please go back and look at those slides to see what do I mean by the absence of symmetry. And that asymmetry is given by the body coefficient M. So this is the body coefficient. So this is given by 1 plus CD by Cox. Ideally, I will want CD to be 0, but that is not going to be possible. So the mitigation strategies was essentially make the gate very thin, or use a different material for the gate oxide so that it has a very high dielectric constant. So these are the two strategies, and this gives us the motivation to choose different device geometries. So now we move to the end section. Just 1 second, please. And now we kind of move to the end section of, yeah, so this session is going to be, as you can see, relatively small. Yes, so, yes. Now, how do we mitigate these, like how do we get a low body coefficient? So this ultimately turned out to be another way to motivate nanoscale devices. Like, why do we need nanoscale devices? So, yes. So one strategy is use a very low doping in the substrate, but this would imply the current values. The negative, the downside of this suggestion is the current values are going to be very low because, of course, the doping concentration is going to be very low. Alternatively, I can use high K dielectrics. Essentially, the oxide layer can be like can have a very high dielectric constant, which will also reduce the dielectrics for oxide layer. So this will also reduce the body coefficient. So that will give us a very strong control of psi s by Vg. Okay, so this is also possible, but this would mean I need to have new fabrication techniques and come up with new materials, and those things are supposed to be considered. And the final strategy is use a very thin gate. So here only the geometry is changing, or have a large surface area gate. Now, if I have a large surface area of gate, that will imply that I have a long channel, and a long channel will automatically imply a high DIBL, drain induced barrier lowering. So this is something that I do not want to do. So the effective strategy was use thin gate devices. Okay. So other important things to remember here, stuff that I did not actually cover in the discussion sessions also, is that we have what is known as the Poisson-Boltzmann equation. So the Poisson-Boltzmann equation is purely theoretical. There were not going to be any numerical problems. So that is why I did not have a discussion of that in the problem solving session. But please go back and revise the Poisson-Boltzmann equation. And as a result of the Poisson-Boltzmann equation, you will have some effects in the 2D electrostatics, where we will consider the doping concentration becoming an effective doping concentration and similar such results. So please go back and revise them from the lecture slides. Sorry, please give me just 1 second. I seem to have got a cold. Yeah. So now we come to the last part where we are considering double gate devices. Extremely so. Now, why do I need double gate devices? Yes, this is something that I also did not discuss. So, what shall I do here? Yes, I will do the following. So, I will quickly get rid of this. And I will select this and move this, or rather resize this. And place this over here. So that way I will have more space to do this. So remember when I was talking about the symmetric relationship, that is going to be this. Yeah. Yes. So when I, oh my God. So when I have the surface charge QS, and this is the surface potential psi s. So in case of a double gate device, I'm going to have a symmetric growth. Okay. So like this. So it's going to be identical on both sides. So I can actually bias these gates in any way I choose to when I have a double gate device. So this is for every double gate device, but the thing that we had a good amount of discussion is for the extremely thin double gate silicon on insulator MOSFETs. So here through double gates, what we achieve is something known as geometric screening. Essentially, when I have two gate terminals here, I kind of make sure that the electric field that is applied by the VDS in this line is kind of not causing any distortions in the electron move. Essentially, what happens when I have DIBL? So let me just go back very quickly and over here make a small diagrammatic representation of DIBL. So what is drain induced barrier lowering? So when I have a potential over here, so when I have a channel like this, and upon the channel I have a gate and insulator, or just gate, it doesn't matter. So let me just say there is a VG. So when there is a VD that is being applied over here, VDS that is being applied across this, then of course there are going to be electric field lines. Now what may happen is that these electric field lines, since essentially when I have two surfaces with different potentials, some charges may get trapped between them, like a capacitor. So that is what will happen if I have. So this again, I've drawn this several times, but I'm just doing it once more, one last time. So then I'll have a straight line. Remember, the job of VDS is to drive electrons from one end to the other. And the direction of these field lines will tell me how the electrons are going to move. Like, after all, that is what field lines are. They tell me what the instantaneous direction of the electric field is. So that will tell me the force that is applied on the electron, the electromotive force, and that is going to tell me which way the electrons are going to move. So as you can see, in this configuration, when I have the electrons entering this channel, depending on the voltage, some of them might just be shot into the gate terminal. They will not reach the drain. From the source, they may just go and hit the drain. So that is not desired for us. So I have the source on this side. So I have the source on this side and drain on this side. Okay. That is not desired. I want all the electrons to move in this direction. So how do I achieve that? One way to achieve that is make the channel length shorter. So that is what we call debye screening. So I have a short length channel, then there aren't many of these curved lines. Most of the electrons will just end up traveling straight. The other kind of screening that I can do is I can have double gates. In that case, what's going to happen is any line that bends upwards will be pulled downwards by the lower gate, and any line that is bending downwards, any electric field line that is potentially bending downwards, will be pulled upwards by the upper gate terminal. So both of these kind of balance the effect. So the average electric field is always going to be from source to drain. So again, last year when we were discussing this course, we had, I mean, even now it is relevant. So the FinFET devices are also multi-gate devices. So they essentially have a three-sided, three-way gate on the channel. And they provide this kind of screening, and that screening reduces the drain-induced barrier lowering that is present in the channel. So another important thing to remember is that debye length, whose expression is given as this, epsilon s into kBt divided by q squared Na, the whole under square root. So I will just change that, because right now it looks like only the numerator is under the square root. Yes, whole under square root. So, and to have good screening, the minimum length should be at least 1/3 of the debye length, the channel length. Okay, so this is the notion of double gate devices. Now, when we are looking at strain engineered devices, so the things that you need to remember, so this is what we did in the very last, not very last, second last week, but I also kind of revisited it in the last week. Remember isoenergy surfaces, remember the notion of subbands. Subbands formed by strain engineering, and also, yeah, so I should have mentioned that somewhere. You know what, I will just go back up and write here in one word. Please refer to the discussion slides. I just realized I skipped one topic on quasi 1D and 2D channels. Now this I have done in significant detail during my sessions themselves. Like, I gave you the exact expressions for the density of states. I even gave the gave the EK relationship, plotted the energy diagram. So all of those things were done in detail. So please go back and refer to them and complement whatever density of states, what is it, like results that you already know. Similarly, the notion of subbands is also present here, but these are subbands caused due to strain. Not too different, like the theory is essentially the same. Again, this I discussed in one example last week. So wherein I have a z directional compression strain, and you saw that the energy spectrum kind of shifted. Instead of having the degeneracy broke, and I had multiple different energy levels. So those are the subbands. In the lectures, they are called the unprimed ladder and the primed ladder of energy levels. So some examples, when I have tensile or compressive strain, I can implement that by depositing silicon on silicon germanium. Silicon germanium has a higher lattice constant. So when it's deposited on silicon, it expresses a compressive strain. So the strain typically reduces the effective mass. Again, I showed how. And a lower effective mass implies a higher mobility. So strain will lead to confinement will lead to subband formation, and subband formation will ensure lower intervalley scattering. Now remember, intervalley scattering implies potential direction change in electron. Like, well, that's what scattering means. So I hope you understand that. Scattering means that an electron moving in one direction turns to another direction. Now, because I'm creating these subbands with distinct energy levels and different electron mobilities, electrons of one mobility will stay in the same band and therefore they will have the same velocity. They are very unlikely to change their velocity, which implies if I have a potential that drives them from source to drain, they will continue to move from the source to the drain. So in the subbands, remember what the primed and unprimed energy ladders are. Please refer to the lecture slides. So I will write that here. And the effective mass, average effective mass relationship is given by 1 by m star average is going to be 2 divided by m star longitudinal plus 4 divided by m star transverse. So this is for tensile strain, unidirectional, uniaxial tensile strain. So if there is a tensile strain in one direction only, along one axis, then that axis becomes your longitudinal axis. So this is where the strain is applied. So this effective mass will become lower. Okay, so here I will also write this m star L would be less than m star T. Again, why it increases or lowers, this I have discussed in the problem solving session. I discussed it as recently as last week. So please go back and go through them. Uh, yeah, there is that. And yeah, so these are the things you need to remember for strain engineered devices. The next part, second last topic, is the quantum dot devices. Sorry. Quantum dot devices are zero dimensional channels. They only have discrete energy levels in them. There are no continuous energy levels. The density of states will always be of this form: g of I, where this g of I is the degeneracy, times delta E minus Ei. This is the Dirac delta function summed over all available values of I. So this is how the density of states will look for a quantum dot device. The ionization potential of a quantum dot device is the highest occupied energy level minus the vacuum energy level divided by the charge. So that will give me the ionization potential. The Fermi energy, now this is true for most nanoscale systems that we look at, it is the energy required to introduce one more electron into the system. So this is what, again, this is something I've discussed during the sessions. This is what is known as the chemical potential. So Fermi energy is equivalent to the chemical potential. They are one and the same. Okay, there is no distinction between them. So again, through examples, I showed how the Fermi energy shifts when the number of electrons present in a quantum dot-like system shifts. So this was numerically shown with example. And then we have the idea of a quantum capacitance. The CQ is given by delta n squared upon delta E. Again, this was explained and a numerical was evaluated for the same. So this kind of brings us to the last topic that we are looking at, which is thermoelectric effects. So again, we go back to the current expression. And we notice that this F2 minus F1 can be made different even in the absence of an applied potential by just changing the temperatures of these two terminals. So that is essentially what we know as the Seebeck effect. So in a Seebeck effect, even when I'm not applying a voltage, when the circuit is kept open, when there is a temperature difference, a potential difference is automatically created. Now, how much this potential difference is? Again, I gave a theoretical sketch in the last session. It was the last one of the last problems that we worked out, and so that is the Seebeck effect. The Peltier effect, on the other hand, is if I have a current moving from here to here, think about it as a Seebeck situation. Electrons will move from the hot region to the cold region because they are carrying heat. So, I mean, in case you didn't know, thermal conduction is also carried through the electrons. Electrons carry heat in the form of kinetic energy and distribute it. So, temperature, like heat, is transferred from hotter bodies to colder bodies. So, if electrons are moving from here to here, then effectively this is considered to be a higher temperature region and this is considered to be a lower temperature region in terms of average kinetic energies. So, the Peltier effect is the temperature difference between the source and the drain as a result of current flow. So when there is a current flowing, a temperature difference will arise. So that is the Peltier effect. And then we have a third thermoelectric effect, which is the Joule effect, where there will be an energy loss as the electrons move from the source to the drain. And the Joule effect is what we see at the source channel interface and the drain channel interface. So these are the three thermoelectric effects. Again, refer to the slides for refer to lecture slides for the expressions, for the accurate expressions. Okay. So yes, this is pretty much a overview, a quick overview of all the topics that were covered in the 12-week course. Once again, I'm not going to quickly, I'm not going to repeat the whole thing, but I will quickly run through from point to point. So start with quantum mechanics. Remember your particle in a box, Schrodinger equation, boundary conditions, and all of that. Then Bloch's theorem is a special condition for a special kind of potential. Everything has been all relevant results are written in this slide itself. Using Bloch's theorem, we solve the KP model, develop the notion of bands, band gaps, then use the EK relationship itself to get the effective mass. And the effective mass gives us some idea as to which kind of electrons participate in transport, which kind of electrons do not. After that, we had a further discussion on density of states. Later on, some weeks after, we considered quasi 1D and quasi 2D materials and, considered how their density of states will look like. So there we first came across the notion of subbands, and then we had a brief discussion about the Fermi-Dirac distribution, the Fermi statistics, and the various properties of the function. Using these quantities, we defined the idea of Landauer model of transport, stored charges, ballistic current, and we defined ballistic transport, the energy loss, or the various physical hallmarks of it, where energy loss occurs, whether there is scattering or not, is there any acceleration. So yeah, that is another point that I missed the first time around. In the channel, the electrons do not undergo any acceleration. They are essentially moving freely. They are free falling. Like they are not in the I shouldn't say free falling. They are moving in the absence of any external force. Whatever their initial velocity was when they were entering the channel, it is assumed that they move with the same velocity unless and until they reach a boundary, another interface. Okay. So low bias case, we have the approximation of the differences between the Fermi distribution functions. We have the Fermi window function, the properties of the Fermi window function, and from that we derive the quantum of conductance. So this quantum of conductance corresponds to around 12.8 kilo ohm. So if I want it to be conductance, I will kind of take the inverse of that. I'm not writing this value here because I've referred to it several times in the previous session. And then For the special 2D case, we got the special relation for the number of modes, gave us an idea of what the minimum width should be so that a channel can conduct current. And that also told us something nice, that the geometry of the system actually determines whether ballistic transport can occur or not. And then we saw the dependence of mode density function to energy, and through that we arrived at the idea of Fermi integrals. We've seen the properties of Fermi integrals, and some more shortcut results are given in this slide. After that, we saw the MOSFET characteristics, and for classical and ballistic. So the classical MOSFET characteristics are things we know. We went back through them, looked at IDS, the output characteristic, the transfer characteristics, derived the notion of saturation velocity, and also had a good discussion about the physical aspects of the saturation, like what happens during channel pinch off, how it occurs, and what it means. And then we have a ballistic. Apologies once again. And then we have a ballistic MOSFET, uh, wherein again the same concepts can be carried over, but we understood that the physicality of the system is significantly different. So once again, to repeat, in a ballistic MOSFET, the gate controls the energy levels that are present in the channel. I will also write it once over here. So in a ballistic MOSFET, gate controls the energy levels in the channel. Essentially, this is what is happening in a bulk MOSFET also, but there are so many energy levels that I will have to treat them as a continuum. But in a ballistic channel, I know I have discretized, quantized energy levels. So even slightly varying the gate voltage will actually cause a significantly larger change in the number of energy levels available in the system. So, and that is also one of the motivations. Like as we have smaller and smaller and smaller transistors, the idea is we kind of can operate many of them at a lower power. So the gate voltages can be lowered to a lesser level so that there is lesser energy dissipation, lesser heat loss, and things like that. So that, and then we saw MOSFET electrostatics, the various results associated with it, and how to mitigate those effects. And that gave us motivation for more nanoscale devices. And certain numerical aspects were also studied, although not in great detail, but nonetheless, please look at them. There may be theory questions based on that. And then one of those strategies was, double gate devices or multi gate devices, strain engineering. So again, we saw some preliminary results, some ideas, how to mitigate screening, how to implement screening, how to reduce DIBL, and then, the control of the gate voltage over psi-s and psi-s over the charge that is stored in the device. And in the channel essentially. And in strain engineering, we were again talking about the notion of subbands came in a device specific context. And then, as I just mentioned a few minutes ago, we through strain engineering, we can achieve lower effective masses and higher mobilities, lesser intervalley scattering, and there are some formulae related to that. So please refer to them and want to see apply them in the numericals appropriately. And finally, we also had a very brief discussion on quantum dot devices, where everything is fully discretized. The transport is not even ballistic; it is fully quantum mechanical because there is no motion of electrons per se. The idea of electronic velocity is lost in a quantum dot device. And over there we saw how the similar concepts are present, how we have ionization potential, how we have quantum capacitance for the channel, and then how to represent the density of states for such a system. So questions for based on quantum dot devices are going to be basic. Like you will not have advanced level questions on that. And so essentially, if you know the results that are given in the lecture slides or in the tutorial discussions, that should be more than enough. And finally, we had thermoelectric effects. So we have three thermoelectric effects: Seebeck, Peltier, and Joule. What they are is written on the slides. I will, refrain from repeating myself too many times. So before I finish, last minute tips. Please go back and revise your assignments. Any questions that you may have gotten wrong, try to figure out what the answers to them are. The assignment solutions should also have been made available to you. If you have any doubts, please post the questions on the forum of the course. We shall be looking at them until your exam date. Although, like, this is the last time I'm interacting with you through these sessions, I will still be going through the course page until the course ends. So I have an obligation to do that. So if you have any questions on the assignment regarding the assignments or any other doubts, please feel free to post them on the forum. We will be more than happy to discuss those things with you through the forum. Uh, and Next, please revise the concepts. Go back, listen to the lectures, listen to the important parts. Like mostly when Professor Vishwan has his slides, if something is important, he will make a note of it on the slides itself. So try to see if you can find the corresponding moment in the videos and listen to what he has to say. Because again, everything that he or I say cannot be written in the slides as we are saying them. That's very time consuming. So there are some things, even in today's session, there are many things that I mentioned that I did not write in the slides. Most of it I tried to write, but some things I've definitely left out. Some I even intentionally left out, hoping that you will come back and listen to these sessions and kind of keep things active and practice some numericals. So practice the numericals in the assignments and vary some of the parameters yourself. Like that is a practice that I had even during the problem solving session. Like many times I will give one question and suddenly immediately change one of those values and try to rework that problem. So try doing those things on your own so that you get a handle on how to deal with numericals of that sort, and that will also give you a nice idea about the underlying math of the things. Like especially one very common thing that I was repeatedly doing was this. Like given a transistor of certain, sorry, not a transistor, a 2D two-terminal ballistic device of certain dimensions, what is the minimum length so that at 0 Kelvin I have any conduction, minimum width of the channel, and what will happen if the width is doubled, what will happen if something else is changed, what will happen if the length is increased, if there is a transmission coefficient, then what is going to happen. So these are things that you can start with one simple problem, and by simply varying the parameters in it, you can kind of develop multiple cases, and you can actually see how each of these edge cases, boundary cases are arrived at. So please practice things to that effect. And other than that, there is nothing more I think I can add anymore, and I will just be repeating myself. So go through the topics well. Just one second, let me get enough. Yes. Go through the topics well, practice your assignments, and practice is key to all of this. Anytime you have any doubts, please feel free to reach out to us on the forums. We'll reply as soon as possible. So with that, I bring my part of my leg of interactions with all of you during this course to an end. I thank you all for your patience and your attention in listening to these sessions. Many of you were and are present in person for these sessions also. Some of you have even been present regularly over the entire 12-week course. So I particularly thank them for their continuous dedication in showing up. And the rest of you, well, you listen to the recorded versions, you have your schedules, you have your life. I want to say, like, do not hold that against anyone. If I were attending a course, I cannot guarantee that I would attend every single session of this in person, which is why I offer particular appreciation to the people who did it. People who couldn't do it, well, it's fine, it's perfectly fine. That is the whole point of having this mode of teaching. I hope these sessions were of some use to you, and even like from my perspective, I can say that doing these things is also very educational for me. Every year, even as I'm doing the same thing over and over again, what I am seeing is every time I repeat these courses, I start noticing newer and newer things. There are things to add, things to remove. As you may have guessed, most of the slides that I use for these sessions are from my previous year's problem solving sessions. But if you, I mean, the slides and the lectures for those sessions are also available to you. They have been shared with you already. If you go through those sessions and my current sessions, you'll see that there is a definite difference, and most of the things that are different emerge on the spot. So it's not that I plan to do something differently and do it in a very deterministic fashion. So it has also been a very significant educational experience for me. And I thank all of you and the NPTEL course framework, NPTEL itself, for providing me with this opportunity. So with that, I wish you all the very best for your upcoming examinations and your future endeavors in life. So for the last time, uh, I will what to say like sign off and end the recording. All the best for your exams and all the best in life. Thank you very much.